In this video, I'm going to talk about inflation, and I want to emphasize the Mexican hat once again. The arrow which says false vacuum points to the top of the Mexican hat, and that's where the universe cools and you have spontaneous symmetry breaking, if you may remember. And we don't know what the top of the hat looks like. It could be flat. And if it's, or at least a little flat. So if it's flat, I want you to think of the universe as coming down energy-wise. When the universe is expanding, the energy is going to decrease. And so when it hits that hat, and the energy is decreased and the universe is inflated a little bit, not much more than a very tiny amount, like the size of an atom, it's going to hit that false vacuum. And if it's at all flat on there, scientists believe that the universe can get stuck up there at the false vacuum. And now look at the difference between the false vacuum and the true vacuum, which is down at 0 on the x and y axis down there. And the difference in energy between the false vacuum and the real vacuum, which is at 0, gives the universe an immense amount of energy, which it uses to expand precipitously. When I'm talking immense amount of expansion in a very short period of time. The universe hyperinflates, if you will, and this inflation that takes place makes this universe unbelievably, staggeringly large in just a few seconds, as you'll see in the next graph. And then a random quantum fluctuation may come along and send us off of the top of that false vacuum, or I should say not us, but send the universe off of the top of that small vacuum, and then it'll stop inflating. But while it's up on that false vacuum, it's just like those ice crystals hanging up there on the false vacuum. On the phase change of the top of the hat. You never would get complete crystallization. You would only get what you're seeing here, a very large difference in energy. And that energy in this case, due to this incomplete symmetry breaking, is expanding the universe quite a bit. And we're talking about exponential growth, and that's what I'm trying to show in this diagram. The equations tell us that the rate of universe expansion is proportional to the size of the universe. So the bigger the universe gets, the faster the rate of expansion. And that's what we call exponential growth, which you can see in this diagram. And I've plotted the scalar factor, AT. You know that that's a measure of the size of the universe, kind of indirectly. We defined it earlier, versus time. And look at how this curve's going. As the universe gets larger, the rate of expansion increases until this is almost going straight up in exponential, or in growth. That is the size of the universe. So this inflationary period is just exceptional. I mean, very few people understand just how amazing this is, or could have been. So, who proposed this? The gentleman on the left, Alan Guth, proposed it in 1979, and he called it inflation. Andre Lin, by the way, on the right, also added to the theory back then. And Guth predicted this inflation during the time when we were having monetary inflation, so he called it inflation, and after the monetary inflation. And I think it's a good name. I mean, literally, we just expanding it at incredible rates. We're expanding, or we expand it at probably by a factor of 10 to the 26. Now, I know you know this, but that's 1 with 26 zeros after. That's a pretty huge factor to be expanding the universe. If we take a look at this graph, it'll give you just some idea of how much. I mean, basically, inflation created the huge universe that we see. Remember, it's 93 billion light years across the visible universe, so this is an immense universe. And that happened within we're expanding today, we're not inflating today, but most of the size of the universe was generated very early on in the Big Bang during this inflation. And if you look at this graph, you can see just how incredible this was. You see time on the x-axis, and of course the distance between any two particles, that's basically what measures space-time expansion. It's happening at just minute fractions of a second. We're getting this inflation. So like 1 second we have just a regular old tiny universe about the size of an atom, and then it expands into the universe we have today, and it's doing that in like, just a minor fraction of a second. We're talking about 10 to the minus 35 and 10 to the minus 32 of a second. Well, that's just an astonishing rate of expansion, and it's like nothing that we can think of today. And one of the nice things about inflation is it helps us explain a lot of the way the universe looks, the physical properties of the universe. Now, I want to talk about our universe for a minute and the way it looks, because this will help you to understand inflation a little bit. If I look off in one direction, we talked about the cosmic background radiation, and we know that'll be about 2.7 degrees Kelvin, and it doesn't matter where I look at the cosmic background radiation, it's going to be 2.7 degrees Kelvin. And also, if I look out in one direction of space, I'm going to see the distribution of mass to be pretty much the same as any other direction I look out into space. Well, that's remarkable. And when physicists see this kind of thing, and astronomers, they say, whoa, wait a minute, everything must have been together at one time in order to have that kind of very little difference in what we see in the universe. We have a isotropic, homogeneous universe, and inflation explains that perfectly. You can think about the universe being on about the size of a very tiny, maybe atom size, and all the energy then, and then just all of a sudden inflating it. Well, everything's in equilibrium before that inflation, and it stays that way when it gets inflated out to these massive distances. So that's a very important thing about inflation. It explains this isotropic, homogeneous nature that we see in our universe. Now, we have to talk about the different shapes of space in order to explore how inflation explains some of the physical properties of our universe. And this goes back to a guy named Alexander Friedman. He's over on the left there. He derived these equations in the 1920s, and he discovered that there were only 3 types of space-time that could exist. And I'm showing them here to you. The first type is a positively curved space. Now, this is a space-time which has an equilateral triangle where the angles will add up to greater than 180 degrees. Now, I know that sounds crazy. We're talking about a universe that's so big, though, that it doesn't matter which kind of space-time we exist in, because the universe is so large that we wouldn't be able to detect the differences in degrees in the equilateral triangle because the universe is so big. But so to us, all the angles add up to 180 degrees. So in the positively curved space, also parallel lines that look parallel, are actually going to cross. You can see how they're crossing at the poles there. So in this positively curved space, it's also going to look like a sphere. It's in the shape of a sphere, and so it's going to be a closed system. This is a funny thing. We have to go back to some things we talked about before, in that mass, remember, affects space-time. Gravity actually we can think of it as matter warping space-time. So the amount of matter that we have in our universe will actually affect what kind of space-time we live in. If there's enough matter in our universe, then space-time will only be able to expand in the spherical universe enough to to go back to out, and then the matter will bring it back down onto itself, and this will lead to a big crunch if we're in a positively curved space-time. Now, we don't have to worry about it because that's gazillions of years from now, but it would be nice to know what kind of space-time we live in. If we live in a negatively curved space-time, this would be the shape of the saddle you see here. And I want to emphasize that the edges here aren't really edges. They go off for infinity in all the directions. And this saddle-shaped universe has equilateral triangles where the angles add up to less than 180 degrees, and where parallel lines actually diverge. If you go out far enough, you can see them diverge rather than be parallel. And this is a kind of universe that doesn't have enough mass in it, and it will expand forever. And then finally we get down to the flat universe, and this is where actually triangle behaves like a triangle. All the angles add up to 180 degrees, parallel lines are parallel, and you may have guessed it, we look like we live in a flat universe. So it's very difficult to tell what kind of universe we live in, and that's because if you think about it, inflation has made this universe so big. If you blew up a balloon and you could shrink yourself down on the surface of the balloon, it would look curved to you. But if we blew that balloon up to the size of the Earth, well, then the balloon wouldn't look curved anymore. It would look flat. And that's what's happened. That's what inflation has done to the universe. Instead of having the angles where we can add them up and decide whether they're less than 180 degrees or greater than 180 degrees, we can't do that because the universe is so doggone big, it's impossible to tell. It looks flat because of the tremendous expansion that it's gone through. Now, we can tell which universe we live in by how much mass is in that universe, as I've already said. And the critical amount of mass is the mass it takes to have a flat universe. That is, a universe that would continue to expand forever but slow down and stop at infinity. God knows what that means. Nobody knows what that means. But that's what the equations tell us. And in a flat universe, you would have a critical density, a precise 9 times 10 to the negative 27th kilograms per cubic meter. Now that is a very small amount of matter. Think about that. In every cubic meter, you've got 27 zeros before you get to a 1 of a kilogram. So that's incredibly small. That's all the mass we're going to need in order to live in a flat universe where the universe continues to expand, but it won't expand forever. It'll stop at infinity. You get the point. It's in between both the curved or the positively curved and the negatively curved. Now, this omega naught that you see here is just the observed density of the universe. That's if we look out into space and we count up how much mass we have out there, then divided by the critical density. So we can actually tell by looking at how much density is out there, we can tell what kind of universe potentially that we live in. And if omega naught is equal to 1, as you already know, then the critical density is the observed density, and we live in a flat universe. If it's greater than 1, we live in a positively curved universe. If it's less than 1, we live in a negatively curved universe. So you would say then, well, let's just go out and measure what the mass is in our universe, and we should know. Well, it's not that simple, as you'll see in just a minute. I want to, though, deviate from this critical matter. I'll come back to it in a few minutes. I want to talk just a minute about the scalar factor versus time once again. This is just to show you what these different spaces would look like on a graph of the scalar factor, AT here, versus time. Now, I'm going to use this graph when we talk about dark energy, and that's why I'm showing you the shapes of the different curves. If we have an empty universe, that means a universe with no mass. It's kind of a reference point there. It's a straight line. And then we have the open, the flat, and the closed. The closed being it'll come back on itself. And remember now, the scalar factor is affected by time. So we're making the measurements now, and that's why they all come together at now on the graph. Just keep in mind that the scalar factor is affected by time. And I'll get into this graph much more when we talk about dark energy. I want to go back to talking about the end of inflation. We got to go back to our Mexican hat once again. And remember, we're stuck up at the false vacuum on the Mexican hat. And that means that for however long we stay at the top of the hat, the universe is going to inflate. Now, you know that we must have come off of that hat pretty quickly right after the universe got to inflating, because we know that the universe expanded within a very short period of time. So something rolled us off. It's generally assumed that some sort of quantum fluctuation, we'll talk a lot more about quantum fluctuations in the next few videos, a quantum fluctuation, remember we talked about virtual particles in the vacuum, those are quantum fluctuations. Well, a quantum fluctuation may have pushed us off, or it's believed pushed us off of the top of that Mexican hat, and we fell down to the real value. And when that happened, it set the forces and the way the forces behave. So in some universes out there, it may have come off in a different direction, and that would have set up the laws of the forces much differently in that kind of universe than in ours. But once the universe comes off of the Mexican hat, it freezes the universe. Symmetry's broken, and it freezes the universe just the way ice crystals freeze the direction in which they grow. You can think of universe freezing the way the forces behave. And that's quite important. I want to emphasize that. This also gives me a chance to talk about the multiverse. You've probably read a lot about the multiverse, and it gets a lot of popular press. And there's a lot of misunderstanding about the multiverse out there, and a lot of different ideas about what the multiverse is. First of all, nobody knows what the heck the multiverse is, absolutely. These are speculations, so keep that in mind. And this is one possible scenario, but it's a scenario that looks very possible from knowing that the universe has inflated. And we can see it all in this graph. All the blue represents our universe. Now, I want you to know the whole graph is our universe, but it postulates that some of our universe, or most of our universe, never fell off of the Mexican hat. It's still inflating, and it's going through that inflationary period. It's a lot like in that video I showed you, where water was freezing. Remember, some of the water didn't freeze during that. The crystals were growing out. Well, this is exactly like that almost. You've got our universe as one of these areas that stopped inflating in the yellow here. And the laws of physics in that universe were set when we rolled off the Mexican hat. But maybe another universe, maybe the one up here in the upper right, it fell off the hat in a different direction, and the laws of physics are different in that multiverse, if you will. So we can have all these sections of space that have gone off of the top of the Mexican hat, and they've stopped expanding, but they have forced nature, if you will, to have physical properties in the way it fell off of the top of the Mexican hat. And by the way, the inflating universe is inflating it faster than the speed of light. So, oh my gosh, you've got this immense amount of inflation. If this is true, just imagine how big this universe. Now you can have space-time expanding faster than the speed of light, but you can't have particles going faster than the speed of light. So this inflating universe at faster than the speed of light is carrying all these universes, or I should say parts of the universe, that have dropped out and stopped inflating. They're carrying them apart from each other. So we could never reach one of those other universes because we can't travel faster than the speed of light, and then they're being carried away faster than the speed of light. Also, remember our whole visible universe is 93 billion light years across. So think about that. I just showed you how little time it took to inflate to these incredible sizes. Just imagine what a universe that's been inflating for 13.8 billion years must look like. Well, I can even hardly imagine it. Just think about the size of this potential universe, and think about all of the sections of this universe that may have stopped inflating during that time. There could be gazillions of these little they're not so little, they're universes like ours, they just have different physical properties potentially. So if you ever want to explain the multiverse to somebody, this is a wonderful way to get the point across. It talks about a very wild place that we live in, and nobody completely understands it. But if we do live in a multiverse like this, then we live in no doubt something that is nearly infinite in size, and we probably have nearly infinite number of these universes or whatever you want to call them, that have sections of our universe that have stopped expanding.